Hello everyone, welcome to my channel. From this video, I will be starting with the sixth module of the subject SPCC, that is System Programming and Compiler Construction. This module is according to the Mumbai University syllabus. Let us see what all topics I will be covering in the upcoming videos. So, according to the Mumbai University syllabus, these are the topics which needs to be covered under the sixth module. In my upcoming videos, you will observe all these topics being covered in detail along with examples. In today's video, I will be talking about intermediate code generation. What are the various types of intermediate code representation? Under that, we will understand syntax tree, directed acyclic graph, that is DAG, postfix notation, and three address code. The remaining topics which are there on the screen will be covered in my upcoming videos. So make sure you are tuned into all my videos. Let us know about intermediate code generation. Just to revise, if you remember the phases of compiler, we have 6 phases of compilation. The first phase is lexical analysis. The second phase is syntax analysis. The third, semantic analysis. The fourth phase is intermediate code generation. This phase is responsible for generating intermediate code, that is a code which is not tied up to any target machine. And this intermediate code generator is responsible for receiving input from semantic analyzer. Let us see what is there on the slide. The slide says, in the analysis synthesis model of a compiler, the front end of a compiler translates a source program into an independent intermediate code. As I said, so the intermediate code generator is responsible for converting the source program into an intermediate code which is not tied up to any machine. It is not tied up to any target machine. The backend of the compiler is then responsible for using this intermediate code and then generate the target code. Thus, the intermediate code is then converted into target code by the code generator. So if you observe, in the logical structure of the compiler, my front end comprises of my parser, my static checker, that is my semantic analyzer, and then my intermediate code generator, whose task is to generate intermediate code. When I talk about static checking includes type checking. That means it is responsible for ensuring that the operators which are applied in any expression are compatible to the operands. The static checking is also responsible to check any syntactic error if there. For example, static checking ensures that a break statement is always enclosed either inside a while loop, for loop, or a switch statement. If the break is not enclosed in any of the mentioned statement, then it should be reporting an error. Thus, the intermediate code generator, whenever is generating an intermediate code, it is assuming that the static checking is already done by the compiler. What is the task of intermediate code generator? As I said, it is responsible for converting the semantic code, that is semantically verified parse tree, into an intermediate code which is not tied up to any machine. Let us understand what are the benefits of machine independent intermediate code. Pay attention students, this can be a theory question for you all. What is intermediate code and what are the benefits of generating an intermediate code? So you can write these points which are mentioned on the slide. The first point is, because the code is machine independent, it is easily portable. You can easily transfer the program or take this program from one machine to another. For example, suppose if a compiler translates the source language to its target machine language without having an intermediate code, then for every new machine we need to develop a new compiler. Say for example, I have written a code in Java. This is just a wild example to make you understand. Suppose I have written a code in Java which is going to generate a target code. Okay, it is not generating any intermediate code. Because it is generating target code, it is possible to execute that code only on that machine. If I take my Java program and try to execute on some another machine, then that machine won't be able to execute your target code. Hence, we will have to develop a new compiler for that new machine. To avoid all these complications, the concept of intermediate code generation was introduced, because obviously there are some modifications in the compiler itself according to machine specification. So from examination point of view, if you are getting a question what is intermediate code and state the advantages of the same, then you can write down the points which are mentioned on the slide. Why do we need intermediate code? Again, so in the previous slide we saw what are the benefits of intermediate code, and in this slide we will be seeing why the intermediate code generation is necessary. So the slide gives you two things, two options to understand. One, what is happening if there was no intermediate code generator, and one, what is happening when there is an intermediate code. So the slide says, assume that I have X number of source language and Y number of target language. That is, assume I am writing my program in C, C++ and Java, and I have 3 more machines on which these program needs to be executed. Because I do not have an intermediate code, each program when is executing on one machine, like say for example, I have 3 programs and 3 machines with me. When my first C program needs to be executed on machine 1, I will need a separate compiler for it. Now my same C program, when I am trying to implement it on second machine, I will need again a new compiler. Similarly, same C program, when I'm trying to execute on my third machine, I will need a new compiler. Thus, for one language, the number of compilers required are 3. Hence, if we apply mathematics, we observe that if there is no intermediate code generated, then the number of compilers required are X into Y. Whereas, if there is an intermediate code, the number of compilers required will be reducing drastically. And again, when we apply mathematics on this concept, you will observe that because there is an intermediate code generated, the number of compilers required will be X plus Y. Let us see what theory is there on the slide when we have intermediate code generator available. In this case, we will need only X number of compilers to convert each source code into its intermediate code. We will also need Y compiler to convert the intermediate code into Y target languages. Thus, the number of compilers required will be X plus Y, which is way lesser than X into Y number of compilers. Also, because of intermediate code, retargeting is facilitated. Retargeting is facilitated means for every machine, we will be using my same front end. So the front end of the compiler will always remain same. What is changing is backend with respect to the target machine. So every time a new compiler is generated for some new machine, the front end remains as it is. The work has to be done only in modifying the backend of the compiler. Also, uh, machine independent is again an important point why we need intermediate code. Because of intermediate code, machine independent code optimizer can be applied to intermediate code. Simplicity is the second need. Intermediate code is simple enough to be easily converted into target code. So ICG reduces the overhead of target code generation. Fifth, complexity. Intermediate code is complex enough to represent all complex structure of high-level languages. So in my upcoming slide, you will understand how an expression is converted into its 3AC format or into its intermediate code. You will understand how a program is converted into its intermediate code. So being a complex structure, it is easy for us to convert this program into its target code. Modification, we can easily modify our code to get better performance and throughput by applying optimization technique to the intermediate code. Thus, we all know that once the intermediate code is generated, code optimization can be easily applicable on that particular output. Intermediate representation. So by now we have understood what is intermediate code. As you know, it is the fourth phase of the compiler. What are the benefits of having intermediate code generation? And third, why do we need an intermediate code generator to be a part of the compiler? Now, we understand what are the various ways in which our intermediate code will be represented. In the process of translating a program in a given source language into code for a target machine, that is, whenever we are in a process of translating a source program which is written in some specific language into a code for a specific target machine, the compiler may construct multiple intermediate representations, and these representations are referred as high level intermediate representation and low level intermediate representation. High level intermediate codes closely resemble the source language, that is, the high level intermediate representation are resembling my source code, whereas the low level intermediate representation are suitable for my target machine. Example given on the slide is syntax tree for high level representation, and for low level it is something which is related to my target machine. Thus, the intermediate representations are of three types: postfix, syntax tree, tree address code. The syntax tree can be easily converted into a new tree which is known as directed acyclic graph. So again, pay attention, students. You can get a question in your viva. See, this subject has a viva for you all. So you can expect a viva question on this. What are the various ways of representing an intermediate code? So your answer is, an intermediate code can be represented in three ways: postfix notation, which is also known as reverse Polish notation. This will be coming in my next slide. Second is syntax tree, and the third is tree address code. We will understand each of this concept in the upcoming part along with the examples. Postfix notations. Assuming you all have already done it in your second year or in the subject of data structure, I will be quickly revising the concept of postfix along with two examples to solve, so that in case if you get a theory on postfix notation or theory on intermediate representation, you can explain your answer with an example. Make sure, students, whenever you are writing any answer, any theory answer in your SPCC subject, always support your answer with an example. This will be helpful for you all to gain more marks for that question. Postfix notation. Why this is one of an important representation of the intermediate code. Compilers find it difficult to distinguish between the operator and parenthesis. So, for this, we have postfix notation in compiler. As I said, postfix notation is also known as reverse Polish notation. In this notation, the operators are written after the operands, not like the infix. Just to revise, infix, postfix, and prefix are three ways of writing an equation. When I talk about infix, is the traditional way we write our equation in maths. A plus B, A minus B is my infix expression where the operator is in between the operands. Prefix, as the word says, prefix, that means the operators appear before the operands, plus AB, minus AB, and so on. Postfix means the operators will be appearing after the operands like AB plus and AB minus. For example, if you observe the slide, in the infix notation, my expression is written as 5 plus x into 7. This will be converted into postfix as 6 plus 7 star. Let us try this example. How do we convert this postfix into this infix into its prefix? My bad. How do we convert this expression into its postfix representation? So let us understand. So whenever you are trying to convert an expression into its postfix, make sure you are using the Bodmer's rule. And according to the Bodmer's rule, if you observe, what I do is I will be first writing my equation for A minus B. Thus, when I convert A minus B into its postfix, I will be writing it as A, B minus. So this is converted into postfix. I put it in bracket so that it's easier for you all to understand. Then I have a star. Then I have C plus D. I will convert it as C, D plus. So as I said, in postfix, make sure the operator comes after the operands. Then I have plus, and then I have bracket for a minus b, which I will be writing it as a b minus. Okay, so this is the basic step. Now let us further continue and solve. So what I do is, this bracket I will be writing it as capital A, this bracket I will be writing it as capital B, and this bracket I will be writing it as capital C, thus updating my expression as A into B plus C. So this is my expression. Now again apply Bodmer's rule and solve. So when I apply Bodmer's rule, this is the first equation which I will be solving. Hence, when I convert this equation into postfix, I am writing it here. Please make sure you are not getting confused. So when I convert this into postfix, it will be AB star and remaining plus and C is not touched. So whatever is underlined, only that is converted into postfix. Now AB star is now referred as D and C is referred as E. Thus, my expression becomes D plus E. And when I convert this D plus E into its postfix, the answer will be DE plus. Now let us get the final answer in the format of A, B, which are there in the original equation. So let us understand. So it is D. Now what is my, see, if you just observe this expression, it is DE plus. Let us see what is my D. Okay, my D is AB star. What is my A? My A is AB minus. What is my B? It is CD plus. And then I have to write a star. Okay, so this is my D. I have written my D. Then it is E plus. Now what is my E? My E is my C. See, my E is my C, which is underlined here. So I replace this E with its C. But what is my C? It is AB. So I will write A, B, and then there is minus, and after that I have plus. So this is my final expression for the given infix to its postfix. I hope this is understood to everybody. Let us solve this example which is on the screen. So as I said, when you start solving, make sure you apply your Bodmer's rule. So what I'll do is I'll just create a rough column over here. Now I'll solve this bracket, and in this bracket by applying Bodmer's parallelly. So when I'm solving it parallelly, it will be AB plus, then the star as it is, then CD is considered as CD minus, the divide as it is. Now when I solve this bracket, E plus F star G, so I'll just solve F star G, I'll keep E plus as it is, and then I have F G star and I keep the bracket as it is. Now if you observe, I'll just rewrite this as A, this as B, and this postfix as C. Hence my equation will be updated as, I'll just write it in rough column. It is A star B divide bracket E plus capital C. Now if you observe, again I have to apply the bracket, I have to solve my bracket. So my postfix expression will be E, C and plus. So I'll just write this into my equation, keeping my AB plus as it is. So I'm not changing A and B anything. So it is A, B and then divide. Now it is EC plus. So E will be written as it is. What is C? It is F, G star and then the plus. Now this will be considered as D. This is A, this is B. Now my updated equation, I'll write it in my rough column. It will be A into B divided by D. So because of Bodmer's, multiplication will happen first. Hence my updated equation will be AB star D, AB star divided by D. Okay, it will be AB star divided by D. So let us see how this works here. It is AB star is A B plus, then B is CD minus, then there is a star, then there's a divide, then there is D. Now this entire equation will become E. Thus I have E divided by D. Okay, and for this the answer will be ED divide. That's it. So let us see. E is what? AB plus CD minus star. Then my D is EFG star plus, and then I have my divide. So this is how you need to solve your postfix expression. Let us see the answer on the slide. It is AB plus CD minus star EFG star plus divide. Yes, the answer is correct. If you practice the way I have taught you, I assume it will be very easy for you, but make sure the practice doesn't stop. It is always practice which will help you to get mastery on this concept. So these are the advantages of postfix notation. The advantages are we need not have any parentheses. If you have just observed, there are no parentheses involved when you write postfix expressions. The evaluation becomes very easier because if you know when we try to evaluate any postfix notation, it is through stack, thus making the evaluation of expression very easy. Parsing can be done very easily because of postfix notation. Lastly, the less scanning is required because there are no parentheses involved in these notations. Uh, Stack is used for converting any infix expression to postfix, but that concept we studied in data structure. Obviously, you can use that concept over here, but because in the subject of SPCC, we need not require that intensely. That is why I have explained you converting an infix to postfix without stack. If you are comfortable using stack, you can go ahead with it. There is nothing wrong in it. It's just that for saving time for the subject of SPCC, I have shown you how to convert it without the use of stack. Coming to next, that is directed acyclic graph, which is also known as DAG. It is a graph for an expression which is identifying common sub-expression. Common sub-expression means any sub-expression that occurs more than once in a given expression. Directed acyclic graph is very similar to syntax tree in the case that for syntax tree as well as for directed acyclic graph, the interior nodes represents my operators, whereas my leaf node will represent operands. The common difference between syntax tree and directed acyclic graph is that syntax tree will be creating nodes for all the operands which are there in my expression. But directed acyclic graph will use those nodes again instead of writing that nodes again. In other words, if I have a node for B, syntax tree will create a separate node for B again in that existing tree. But directed acyclic graph will reuse the node B which was already created. This will be more clear when I take an example on my next slide. Thus, a DAG not only represents expressions more succinctly, it gives the compiler important clues regarding the generation of efficient code to evaluate the expression. Thus, the directed acyclic graph is going to help the code optimizer to optimize the code very easily. To understand the concept of directed acyclic graph, let us solve an example. So this is the example for which we need to create a DAG. Before jumping on for creating DAG, we will first identify the common sub-expression which is there in the equation. If you observe, B minus C is an expression which is repeated in the given equation. Hence, B minus C is considered to be common sub-expression elimination. Now, before jumping on to creating a DAG, I will suggest everyone to first create a 3AC. Creating a 3AC and then converting it to DAG gives an easier way to solve your given question. So, whenever we are creating a DAG, I will suggest everyone to write 3AC and then convert it to a DAG. Whenever we are given any equation and we are supposed to write its 3AC, we start with the concept of Bodmer's. That is, we apply Bodmer's rule on the given equation. And thus, because I have to apply Bodmer's, my first equation in my 3AC will be T1 is equal to B minus C. B minus C is calculated and the result is saved in T1, thus making B minus C nothing but, I will rename this B minus C to T1. Okay, so this is T1 over here, this is T1 and this is also named as T1. Now if you observe, in my next step I have to multiply A and T1. Thus I will be writing A into T1 and the result is stored in a temporary variable. Similarly, the next what I will perform is T1 into D. So T1 into D is the next equation to be solved. I will store that result in T3, thus making this equation to be called as T2 and this equation now to be referred as T3. Next in my 3AC it will be T4 is equal to, now I will add A and T2. So I will write T4 is equal to A plus T2. Then I have T5. T5 may, if you observe, this is what is my T4. This is my T3. So it is T4 plus T3. So this is my 3AC. Let us convert it into DAG. So I'll start with my first equation, that is B minus C. Let us create a tree for this. So as I said, the operands becomes the leaf node and the operator becomes my root node. Okay. Now because it is a 3AC, because it is a DAG graph, I will rename my root node as T1. Why T1? Because the left hand side of this equation is nothing but T1. So I'll just rename my node as T1. You can also do it in your exam. You can write it in pencil, making your task easier. Next, if you observe, I will be creating a tree for A into T1. Now if you observe, T1 is already existing. A is on the left hand side of T1. So it is A and this T1, this node is named as T1 now. So A and T1 needs to be multiplied, thus making this as a tree with star as my root node, A as my left child, T1 as my right child. Again, whenever I create a tree, I will rename my root node. Now this root node will be renamed as T2. Let us go to the next equation, that is T1 into D. Again, if you observe, T1 is existing, D is on my right hand side. I have to perform multiplication operator and I will connect this. Again, star will be renamed as T3. Next it is A plus T2. Okay, if you just observe, it is A plus T2. Pay attention, because it is a DAG, I will not create a node for A because it is already existing. I will not create a node for T2 because it is already existing. So how do I do it? I'm doing it with red so that it is understood. A is a node which is already existing. So I take that node. T2 is a node which is already existing. I take that node T2. What is the operation between A and T2? The operation is plus, making this node to be named as T4. Okay. Now the last equation in my 3AC is, T4 plus T3. Now where is my T4? This is my T4. This is my T3 and there will be an addition operation over here. So this is how your tree is created. I will just change the name over here so that it is visible. So this was T4. So this is your DAG for the given equation. I hope the example is clear. Let us take one more example to make the understanding more clear. The example I'll write over here. Okay, so let us take this example. The example is, it is A into B plus C minus D star A star B plus B. So we have to create a DAG. This will be my rough column. What we have to do is identify the common sub expression. So yeah, if you just observe A into B is the common sub expression because that expression is repeated twice in my given equation. And if I want to convert this into a 3AC format, I apply BODMIS. So T1 is equal to A into B and T2 is equal to C minus D. Thus, I will rename this as T1, this will be T2 and this will be T1. If you observe according to BODMIS, it will be T2 into T1. So, I will be doing T2 into T1 and giving it a temporary variable. Thus, this particular thing which is in the square bracket or square for now, I will call it as T3. Now, if you read the equation, it will be T1 plus T3 plus B. So, all additions are there, all operators are of same priority. Hence, I will add T1 and T3, storing the result in T4. And finally, it will be T4 plus B, storing the result in T5. Let us start creating a tree. So, we'll first create a tree for A, B into, okay, this will be named as T1, then it is C D minus, here minus will be referred as T2, the root node will be referred as T2. Now it is T2 into T1. So okay, I'll do it as sorry, not to erase this, it will be T2 into T1 and this node will be named as T3. Then it is T1 plus T3. So if you observe T1 and T3 over here, and what I have to do is I have to add. So I'll take this T1 node, I'll take this T3 node, and I will add this, making this addition node to be named, of naming this addition as T4, and then it is T4 plus B. So how will I do it? T4 is here, so it is T4, sorry, it is T4, where is B? B is existing, so I can just take a path from here and it is T4 plus B. And this final node is named as T5. So this is one more example where I have explained you how to convert a given equation into its DAG format. Let us take the last example on DAG. So the equation for this is x is equal to, uh, sorry, let me erase this. It is minus a into b plus minus a into b. So let us identify the common sub expression. So if you observe, this is unary minus a into b and this is again unary minus a into b. So this is my common sub expression. Before again going to DAG, we will first create our 3AC. So whenever we are creating 3AC and following the BODMAS rule, make sure the unary operator minus gets the highest priority. Thus, I will write my 3AC for unary minus in this format. T1 is equal to U minus, U stands for unary, U minus A. Okay, then I will multiply unary minus with B, thus making my another equation T2 is equal to T1 into B. Thus this entire expression is T2 and this sub expression is T2. I will have to add it. So it is T2 plus T2, and result goes in a temporary variable T3. Finally, I will write x is equal to T3. Let us create our DAG. So I will start with U minus. It's a unary operator, so it is U minus A. This U minus will be named as T1. Okay. Next it is T1 into B. Lack of space. I'll just erase this. I'll make it little aside. T1 into B is my okay. So T1 into B is my next equation for which I will be drawing my DAG. So B is on right hand side. So I'll keep B here. It is T1. I take T1. I take B and I multiply it by I multiply it, making this star node to be referred as T2. So this will be referred as T2. Next, if you observe, it is T2 plus T2. Thus, I will take left. This is T2 left. This is T2 right. And the operation between them is addition, that is plus. I will name this root as T3. Finally, it is x is equal to T3. X being on left hand side, I will have x here, I will have equal to here, and I will join this, naming this as my final tree. So this is my final DAG for the given equation. I hope everybody have understood. Directed acyclic graph for expression. So this basically is a slide which is added in case if you are getting a theory question on DAG. So if you get a theory question on DAG, we expect that this slide is written. You also write the applications where DAG is useful, and you can mention any one example which I have taken previously. Let us understand the applications of DAG first. To determine the expressions which have been computed more than once, that is because of DAG we can easily identify the common sub-expression. To determine the names whose computation has been done outside the block but used inside the block. To determine the statements of the block whose computed value can be made available outside the block. Last, to simplify the list of quadruples by not executing the assignment instruction unless they are necessary and eliminating common sub-expression. So if you get a theory question of say 5 marks or 10 marks for DAG, you are expected to write the theory slides. The first slide before examples, then I took 3-4 examples and the other 2 slides. So this 4 slides will be helping you to create your 10-mark question. In my next video, I will be explaining you how to create 3AC for a code. So given a code snippet, how that code is converted into 3AC, that I will explain. What are the concepts of quadruples, triples, indirect triples, and what is SSA? All these concepts will be taken in the next lecture. These concepts are very important from examination point of view. You can always expect a 10-mark question on either DAG or intermediate code representation or quadruples or triples, and yes, you can also expect a numerical on the same. Thank you for your patience listening. Meet you all in my next video.